All right, so we're going to go over sections 8.8 through 8.9 for Chemistry 1151. So we talked about solutions already. We've talked about different ways to calculate solutions, dilute solutions, and what consists of a solution. But there are some different properties of solutions that change from the pieces. So, for example, salt water doesn't behave exactly the same way as salt does or water does. And so the salt changes the properties of the water. Um, and the way that it changes is through something called a colligative property. So colligative properties are properties of a solution that they depend on how much we have of the solute, but not its identity. So for example, if we wanted to raise the boiling point of water, which is what we do when we're cooking, you're cooking pasta and you throw salt in there, you could actually raise the boiling point of water by putting in sugar. It won't raise the boiling point of water as much as salt, and then we can talk about why. But you could pour sugar into your water and it would still raise the boiling point a little bit. It wouldn't raise it as much as the salt. Now, if you wanted to raise your boiling point even more than sodium chloride, we could put in maybe magnesium chloride, something that gives us more ions. Or you just make it more concentrated. You wanna make the water boil really, really high temperature. You want to cook the pasta in a really, really high temperature of water before it starts to boil. Then you put in a lot of salt to your water. If you only want to raise it a little bit, we put in a little bit of salt. So the amount of the solute tells us what's going to happen to the property, but not the identity. Again, you could put in sugar and you could still raise the boiling point. We don't do that, right? But you could, technically, you could do that. Um, so the number of dissolved particles affects the properties. So for example, sodium chloride, when it dissolves, breaks down into two particles, sodium and chlorine. It's a strong electrolyte. So it breaks into two particles. Versus if we were to look at magnesium chloride, magnesium would make two chlorides, and so it would break down into three particles. And so even if we had the same amount of sodium and magnesium, like the same moles of sodium chloride and the same moles of magnesium chloride, the magnesium chloride would raise my boiling point more because it's more particles. And then if we think about like sugar, so I'll just say sucrose solid turns into sucrose aqueous. It's just one particle. It didn't break into pieces. It's a non-electrolyte, so it didn't give us more than one particle. So sodium chloride, one particle turns into two particles. Magnesium chloride, one particle turns into three particles. Sucrose, sugar, one particle turns into one particle, right? So does it affect my boiling point? Yes, but not as much as the strong electrolytes, which break into more pieces. Some properties that the addition of solute affects are the elevation of the boiling point, so raising the boiling point, lowering of the melting point, also lowering freezing point. So freezing point and melting point, same thing, aka freezing point. And you might know about lowering the freezing point and what we do in winter to the roads. We lay salt down on the roads, salt the roads. This lowers the freezing point, which makes it harder for water to freeze over on the roads. So it has to be even colder for it to freeze. Elevation of boiling point makes it harder for water to boil. So it has to get up to higher temperatures to boil, which means you're cooking your pasta in higher temperatures, which means it'll cook faster or better or whatever you desire by having it in a higher temperature. And then also the pressure due to osmosis. We'll talk about that a little bit later. So first, let's hone in on the boiling point elevation for a moment. A volatile solute rapidly escapes into vapor. So vapor is gas. Um, we call it volatile if it um, likes to become a gas easily. So, for example, gasoline is volatile. If it's something where it's a liquid but you can smell it, it's probably volatile, like acetone, nail polish remover, alcohol, gasoline, these things that turn into fumes, right? That's a vapor, and that's a gas phase. Non-volatile solutes don't really escape, and so it doesn't have a vapor pressure. So we talked about vapor pressure before, but vapor pressure basically is how much pressure the gas version of a liquid has. So the easier it is to turn into a gas, the higher the vapor pressure. Volatile, high vapor pressure. Non-volatile, not really any vapor pressure at all because it's not turning into gas. So vapor pressure above the solution of a non-volatile solute is lower than the pure solvent. And so a adding, so for example, a volatile solute would be like gasoline, which is octane, so just a gasoline, which is a nonpolar carbon hydrogen molecule. It has London dispersion forces only. So it's got pretty weak forces, so it's pretty easy to turn into a gas. So it's easy to turn into a gas. Non-volatile would be like sodium chloride. This is ionic. Very strong forces hold it together, right? Not even, we don't even talk about this in terms of intermolecular forces. It's like beyond that. So very strong forces hold it together. It's not turning very, very, very high boiling point. This thing is not turning into liquid. It's not turning into gas anytime soon. And so it's very non-volatile. You don't think about sodium chloride turning into gas ever, right? We don't even consider it really turning into a liquid. We talked about this, I think, before, but if you turn sodium chloride into a liquid, we call it molten, like lava, because it has to get that hot to liquefy it. So adding something like NaCl to water makes it harder for water to evaporate. So this lowers the vapor pressure because there's going to be less gas now. So the reason why it does this is because adding NaCl adds in those charges, and water is super attracted to these charges. So the water has positive and negative ends to the molecules, and they really like those charges. So they're going to hang around with those charges. They're not going to go turn into gas. They're going to stay liquid so that they can be around the things they're attracted to. So you don't have to get into too much detail with all of this. Just know that if you add something, you're lowering the vapor pressure, you're making it harder to evaporate. And so if it's harder to evaporate, it takes it longer to boil. That's a higher boiling point. And we talked about this already, but the amount the boiling point increases depends on the number of particles. So if we put in sodium chloride, it dissolves into 2 particles. We could make the boiling point go up even more if we added magnesium chloride, which has 3 particles. 1 mole of any non-volatile solute, this is any ionic compound pretty much, raises the boiling point 1 kilogram of H2O, about the same amount, about 0.51. Okay. Freezing point depression is just the opposite. It makes it harder to freeze. So boiling point elevation makes it harder to boil. So we got to have a higher temperature to do that. Freezing point makes it harder to freeze. It's got to be lower, got to be colder. So freezing point depression says that a non-volatile solute usually has a lower freezing point than the solvent alone. I mean, it takes, you have to, if you, sodium chloride, for example, is salt at room temperature, is solid at room temperature. Water is not, so it has a lower freezing point than the water. So it, wait, um, oh no, uh, hold on. This is a liquid solution that contains, oh, Not the non-volatile solute doesn't have a lower freezing point. That's false. The liquid solution has a lower freezing point now than the solvent alone. That's the point. So sodium, so salt water has lower freezing point. This is a confusing sentence than pure water. So it takes the water more time to freeze, meaning you have to pull more energy from it. It has to be colder outside for the water to freeze. And that's good because we don't want water freezing on the roads, so we can salt the roads. And again, this happens for the number of particles. But we can think about it as a number 1.6 for 1 mole to turn 1 kilogram of water, 1.6 degrees Celsius. You don't need, I don't think you have to do any math with those numbers. Maybe in Alex, but definitely not on the test. And last little topic here is osmosis and dialysis. So before we can start talking about osmosis, we got to make sure you understand what a semi-permeable membrane is. A semi-permeable membrane is semi meaning partial, permeable meaning able to go through. So a semi-permeable membrane means that some things can go through it and some things can't. It's like a filter. Okay, some things can go through it, some things can't. Semi-permeable membranes will get water and small molecules to go, but ions and large molecules cannot go across it. And our cell membrane is a semi-permeable membrane. Osmosis is the passage of a solvent, usually water, across a semi-permeable membrane. It always goes from low concentration to high concentration. We flow from low concentration to high concentration. The water, the solvent or the water, always wants to be where more solute is. They want to be where the party is. Oh, there's more solute over there. It's going to go over there. So for example, if you have, let me show you an example. So example here, if we have only water on the right side and we got some of this solute, whatever this is over here, water is going to flow this way because it wants to go be part of the party and it's trying to dilute the other side. It's trying to make the two sides equal. If there's stuff over here the water can dissolve, the water is going to flow over to that side. Now, the big molecules, this solute, cannot flow this way because the semi-permeable membrane is too small of a hole for it to go through. It won't let it through. Osmotic pressure is the pressure that prevents the flow of additional solvent into a solution. So eventually we'll move over water, and at some point the water will stop moving over because the pressure on this side will get to be too high and the water level won't be able to, we won't be able to move. It's not, this side is not going to be dry, no water eventually, right? It's going to get to a certain point where it can't go anymore because there's no more room. The pressure over here is too high. There's no more room for water to come in. That's the osmotic pressure. Again, you don't need to worry about doing math or anything with this. It's just definition stuff, okay? So for example, semi-permeable membrane, if only water is over here and you've got glucose over here, the water's gonna be like, oh, the party's over here. Water's got really bad FOMO. It doesn't want to be left out of what's going on with the solute. So water's gonna travel across, but then at some point it's gonna stop moving across because there's gonna be not enough room here for more water to come in. So then you have equilibrium where some water comes out and some water goes in, but at the same rate, it'll just kind of stay that way. That's because the osmotic pressure is the difference between this is the max that it can get. Okay, we won't be able to put any more water to the right without taking some water out. So, what does this mean for us as far as the human body, our cells? And so this is actually pretty relevant to those of you going into healthcare or nursing. Two solutions with the same osmotic pressure are called isotonic. And so I want to, tonic meaning like the solution, I guess. Iso means same. So iso means same. A 0.92% weight volume sodium chloride solution is isotonic to our bodies. And a 5% glucose solution is isotonic to our bodies. So if you are working in a hospital or doing rounds or at a clinic or anything like that, I bet if you look at an IV bag of saline, it will say 0.92% or 0.9% weight volume or mass volume in ACl solution because it's isotonic. You do not want to inject pure water into someone's bloodstream because it is not the same isotonic as the environment the blood cells are already in. So with an isotonic solution, we get this equilibrium. Some water goes in, some water goes out, but the amount of water on each side doesn't actually change anymore. We get an equilibrium state where the amount of water on this side, the amount of water on this side, it stays the same, and we just have water kind of going back and forth, but at the same rate. So if one water goes in, another water goes out. Same thing happens to the cell. If it's an isotonic solution, the inside of the cell concentration is the same as the outside of the cell concentration. So water goes out, water goes in at the same rate. Water's not rushing out of the cell and not rushing into the cell. And that's going to be true of both of these situations. And so I think you would need to memorize these two numbers so that you can tell if something is isotonic or not. Now, what if we need there's medical reasons for this, but a hypotonic solution, hypo meaning less than, like hypothermia, right? Less than. So lower osmotic pressure, also lower concentration than isotonic. So what would that be? Lower concentration for isotonic would be less than 0.92% sodium chloride weight volume or less than 5% weight volume glucose. So if you give someone an IV of 0.5% sodium chloride, that would be hypotonic. What happens hypotonic is that if this is, let's say that inside the cell is 0.92% sodium chloride and outside the cell is 0.5% sodium chloride, water wants to flow toward the higher concentrated area. So water is going to be like, oh, there's a party inside here. All the sodium chloride is in here. So water will flow into the cell. But there's not going to be any water flowing out of the cell until we reach osmotic pressure. So water's going to flow into the cell and it's going to make the cell swell. So the cell will swell and eventually, if it's different enough, the cell can burst. We call this hemolysis. Heme meaning blood cell, right? And lysis meaning split or open up. So hypotonic, you can think about it as the O of hypo is what our cells will look like, really round and swollen. So hypotonic solution would make hemolysis for our blood cells because water is going to flow into the cell because it's less concentrated outside. There's more water outside the cell than inside the cell, and water is going to flow in there to go where the party is, to go where the more concentrated is. So hypotonic hemolysis is swelling of the blood cell if you're in a solution, a hypotonic solution. Opposite of that is a hypertonic solution. So hyper meaning more. So hypertonic has higher concentration. So higher concentration than isotonic. So this would mean greater than 0.92% sodium chloride and greater than 5% glucose. So let's say this is 10% glucose on the outside and on the inside of the cell, it's 5% glucose. Well, the water inside the cell is going to go, if there's a party out there, there's a lot of glucose out there, I need to go dilute it. So the water will leave the cell. When the water leaves the cell, it shrinks. It shrivels up. It gets dry, right? We call this crenation. So a hypertonic solution causes crenation. And I remember what it looks like by looking at the R of hypertonic. Kind of looks like a shriveled up little blood cell. So the O of hypotonic, that's what my blood cell does. It's rounded, it swells up, it gets big, it can lyse, it can be broken apart. The R of hypertonic is my cell like shriveling up because it's gonna not have any water in it. And then all of this osmosis stuff is used for dialysis. And so the body has a natural movement of water in and out of our blood, but we also can push through, um, we can push our blood through filters and things like this to filter out the stuff our kidneys should usually filter out. So this whole machine filters out our waste using osmotic pressure and osmosis. There's semi-permeable membranes all in this, and they don't. Unfortunately, it's not really showing you exactly what those things are. But the waste particles can come out of the blood, but other important stuff doesn't come out of the blood. So as your blood goes through the dialysis machine, it um the waste particles come out because the semi-permeable membrane in these tubes um, allow the waste particles to come out and allow like water to maybe flow in, and then so it cleans your blood and then it puts your blood back into your body. That's it for this video. I'll see you later.